Today it's my pleasure to present to you Adriana Figueroa, which, well, she does not really need a presentation at home because Zaragoza is and will ever be her home, as she arrived to Zaragoza in 2008 with CSIC grant, high predoc grant, to perform during 4 years her PhD studies under the supervision of Professor Juan Bartolomé and Luis Miguel Garcia. She defended her PhD thesis in 2012, and which was a really brilliant thesis. And indeed, it was accepted by Springer in the series Outstanding PhD Research as a book that you can always buy and enjoy. After her 4 or 5 years in the end with us, which we really enjoyed, she went to her first postdoc to the synchrotron source Diamond near Oxford, where she was contracted with Gerrit van der Laan's group for 4 years. She really did a very good work under Gerrit van der Laan's guidance, and for example, among many other papers, they too wrote a review on synchrotron radiation and magnetism techniques, which is a highly cited paper. After those 4 years in Diamond in Oxford, she came back to Spain to ICN2, the Catalan Institute of Nanoscience. She arrived there in 2017, and she's still there today. There she has privileged 2 very competitive grants. First, the Juan de la Cierva grant of the Spanish Ministry of Science, and afterwards Marie Curie Slodowska mobility grant of the European Union. As far as I know, she's since 2 weeks ago contracted under Sergio Valenzuela's group, which is the group where she has been working these 5 years there at the ICN2. Okay, in order to be not too long, I could extend more talking of Adriana, but it is her time, not mine. So I will let her to give her seminar, Spintronics in Topological Insulators and 2D Materials, Interfacial Phenomena. Thank you, Adriana, for coming home back again, and it's all yours.
Thank you very much, Fernando. It's such a pleasure for me to be here, at least virtually. It's an honor to have been invited to this prestigious series of conferences, of seminars of the condensed matter physics department. I remember I enjoyed a lot this series when I was there as a PhD, and yeah, I agree. I mean, I cannot agree further more than Zaragoza is my home too. So I'm really happy to be here, and I want to thank you and to thank the organizers, me, Pepa, and David, and the whole department to welcome me again, and for this invitation. It's really a pleasure. And thanks. Well, I'm going to make a start. I'm going to give you an overview of what I'm working right now at ICN2. So as the title says, it's about spintronics and 2 kind of materials, topological insulators and 2D materials. And I'm going to focus on this research, this investigation of interfacial phenomena that we're doing and how that affects the spintronic properties of these materials. But I'm going to start by introducing a bit what we do at the group. So as you said, Fernando, I work at the group of Sergio Valenzuela. It's the physics and engineering of nano devices. So this is a not very up-to-date picture because it's not very updated. Last year we were supposed to take a more a new one with more members. I mean, right now in this picture there are a few members who are no longer there, but yeah. And also we have more women now. It's not only me. And in our group we focus on, let's say, there are like two divisions, like two research lines regarding two types of materials. One is about topological insulators, which is the one that I basically like mostly work on. And in this research line, we do epitaxial growth of TIs, topological insulators of this family of materials, bismuth, antimony, selenites, and tellurides, and so on. We do in situ and ex situ characterization, and we also integrate these thin films that we grow onto devices to do magnitude transport, speed torque FMR, and also to do advanced characterization via synchrotron radiation facilities, for example, at like X-ray absorption spectroscopies or also photoemission spectroscopies. And more recently, we are also incorporating a new tool for characterization of their ultra-fast electronic properties with terahertz spectroscopies. And then on the other research line is based on graphene and 2D materials. And then the group focuses on mechanical exfoliation and stacking. I mean, to do van der Waals heater structures using these kind of materials. They incorporate them into device fabrication as well. And in particular, to study spin-related transport, I mean, spintronics and thermoelectricity on these materials, right? And then just to give you a brief, an overview of what kind of materials we study, we want to study or like to investigate the interplay between, different combinations of 2D and topological materials. So we have graphene on the one hand, it has a weak spin orbit coupling, but if we combine it with other materials that have a strong spin orbit coupling, like topological insulators or transition metal nickel coordinates, which are 2D materials as well, we can exploit the electronic properties and spintronic properties of such heater structures and try to build or like to develop devices that are relevant or like have potential applications for spintronics or even electronics, like modern electronics, in the sense of using more efficient, to have energy efficient devices, right? We are also incorporating to our tool, or like to our toolbox of not toolbox, but let's say to our portfolio of materials that we are researching on is 2D magnets as well. So we have like a bunch of van der Waals materials that can be incorporated into such as heater structures and in the future to devices. Right? And why do, what kind of area, what's the area of our research where we are focusing on? So our research is devoted to spin orbitronics, in which is beautifully described as the art of manipulating spin orbit coupling, about manipulating spins with spin orbit coupling. As I said, we have a series of materials that can be used for applications of spin orbitronics, which is like, say, beyond the spintronics applications. And in this case, as I told you, I'm talking about direct materials and topological insulators. And in these applications, what we want to do, like in this area, what we want to do is to understand, control, and manipulate the spin to charge interconversion that happens at these kind of materials, at the boundaries of these kind of materials, and also at the boundaries and in combination when they are part of heterostructures. And so we are interested in what happens, on understanding what happens at the interface, and also to manipulate those phenomena at the interface. And that's why it's very, very relevant to have a control of that interfacial phenomena, and also an understanding of that interfacial phenomena. And that's why we require advanced characterization techniques that allows us to unravel what happens at those interfaces, and also to understand at the microscopic level that what happens there, because that way we can have an efficient control of the spin to charge interconversion. So as I said, I focus on these two kind of materials, and that's what my presentation is going to be about. So I'm gonna give you some recent results that we have had about the use of advanced characterization technique to study, to explore the interfacial phenomena that occurs at interfaces of topological insulators with magnetic materials, and also at the interfaces of graphene and 2D materials, and especially address to understand what happens with the spintronic properties of those interfaces. So in terms of, regarding the topological insulator part, the first part, I'm going to show you how we can do some interface engineering to control the spin orbit torques on TI's interface with permalloy, which is a conventional metallic ferromagnet. And I'm going to also show you how X-ray absorption spectroscopies have allowed us to find information about the proximity effects that happen at the interfaces of TIs with magnetic insulators. And then on the second part, the second part is going to be shorter. So I'm going to show you how also these X-ray absorption spectroscopies have allowed us to understand and to study phenomena at the interfaces of of graphene with transition metal decalcogenides, in this case MS2, in order to explore the spin orbit coupling in these hybrid structures. So I'm going to start with the first part, which is the topological insulator. So just briefly to give you an introduction about what a topological insulator is, it's going to be very brief. A TI is characterized electronically by its bulk insulator properties, but it also has, coexist with topologically protected conducting surface states. So some people, a very naive explanation of a TI, of a 3D TI, they describe it as a brick, which is insulated in the bulk, that is wrapped in an aluminum foil that is conducting, because you have those metallic-like surface states at the surface. But of course, it goes beyond that, because those surface states are topologically protected. But what you see on a band structure of a topological insulator is exactly that you have a bulk band gap that coexists with those surface states that are metallic-like. And those surface states are characterized by the spin momentum locking that are protected by time reversal symmetry. And all these characteristics of the TI is because, they are a consequence of the large spin orbit interaction. And that's why these are very, they are materials that are very attractive for application in spintronics and spin orbitronics, okay? And what we do at ICN2 is to grow topological insulators, thin films, using our machine of molecular beam epitaxy. So here I'm showing a picture of the growth chamber that we have in our lab. So it comprises two growth chambers. One is dedicated to the growth of TIs of the family of bismuth, antimony, tellurium, and selenium. So we call these like a dirty dirty chamber, sorry, because this is where we have the chalcogen atoms to grow our TIs. And we also have some transition metal atoms here that we use for doping or to make some magnetic TIs as well. And then the nice thing about this chamber is that it's connected in vacuum through this vacuum tunnel to a second chamber where we can evaporate other materials that so in this chamber we're dedicated to metals and oxides and some insulating materials. So in this chamber, we can evaporate, for example, magnetic materials such as permalloy, cobalt, or europium sulfide. At ICN2, we also have, facilities that allow us, laboratories that allow us to characterize and do processing of devices. So we count with clean room facilities, nanofabrication facilities, other e-beam evaporators, and characterization facilities like X-ray photoemission spectroscopies or angle resort photoemission spectroscopies and X-ray diffraction as well. And there's another feature that I want to mention here, which is relevant for the growth of heat structures of the topological insulator thin films, is that we also count on a UHP suitcase transport system where we can take our samples that we grow here on this chamber, that means, say, for example, our TIs, and transport them in vacuum, in ultra high vacuum, to other chambers or other facilities, not only at ICN2, but in other labs, for example, to Alba synchrotron or to other characterization facilities or equipment, like to do scanning tunnel microscopy or XPS, or to grow other layers like PLD, and not only to transport them from here to there, from there to here. Okay, so I'm going to give you just a brief introduction about the kind of quality of the thin films that we grow. So this the growth of the TIs was developed by Frederick Bonnell in our group. He was a former senior researcher in the group. And then he managed to grow very high quality thin films and to develop the growth so that we could use the recipes for our thin films and our heat structures. So this family of TIs has a crystal structure that is layered. It's rhombohedral of this space group. And then it's characterized by this, what we call this basic unit is called the quintuple layer, because it comprises 5 layers, one layer of tellurium or selenium, then one layer of bismuth or antimony, another chalcogen, then bismuth antimony, and then it finalizes with another chalcogen layer. And then these quintuple layer units are bounded to the other quintuple layer by van der Waals forces. So the nice thing is that these are layered materials, and that can be grown in several kind of substrates. But of course, the quality of the layers is depends on the mismatch between the substrate and the layer that you grow on top. So the best results has been obtained with the substrates of barium fluoride 111, where it was developed that for some conditions to grow at a given temperature of the substrate, to make sure that the surface of the samples of the thin films are very, very flat, or like at least that you can remove, try to suppress the roughness, or not suppress, but like to reduce the roughness. And also the other characteristic that was obtained was that there was a suppression of the twin, the presence on these TIs, which is really, really useful for transport applications. right? And in terms of transport, say like magnetotransport in these thin films, this is what we are interested in. We are interested in understanding, or like in controlling and make sure we can exploit the transport properties of the TIs to make sure that we can exploit those surface states that are happen at the surface of these thin films. But what happens is most of the time is that you have a combination of in these TIs that have a combination of bulk and surface transport, because there's usually contribution of bulk carriers in the material. So what we want to do is to make sure that we can reduce such contribution of bulk, and that can be done by adding to bismuth telluride, for example, that is TI, you add some sort of doping of antimony atoms, so that you're able to tune the position of the Fermi energy in the gap, so that you make sure that your material is insulating, and then that your transport properties is basically done, or like is mostly done by the surface states of the TI, and that is obtained at about a concentration of about 60%. And this is relevant because this optimization was performed as well by Frederic Bonnel. And then we can make sure that with this concentration, we are obtaining the optimal properties in terms of magnetotransport for this kind of material, this BST, bismuth antimony telluride alloy. And then that way we can incorporate it into our devices to study even more properties of it. And then there is another point that I like to point out here, which is that you want, for transport, the other requirement, or an important requirement, is that you want minimal interaction with the interlayers that you have these TIs with, because it's demonstrated that there is hybridization, still hybridization between the TIs and metals, because of it's usually, and then not only with metals but with the ferromagnetic metals, there is usually a magnetic lead layer that happens at the interfaces with the TI, and that is also, I mean, that is relevant not only for like transport itself, but also for spintronics, and that's one of the first let's say results that I wanted to show you and to talk to you about. This is a study about spin orbit torques at the interfaces of TIs with ferromagnetic materials. So in this case, we used a spin transfer torque ferromagnetic resonance to study the spintronic properties, I mean the spin orbit torques that are generated at the interface of the TI, in this case with a permalloy, which is a metallic ferromagnet, So what happens is that if you pass a current through your TI, there is a significant non-equilibrium spin density at the boundary of the TI as a consequence of the Rashba-Aldenstein effect, that is also known as the inverse spin galvanic effect. Okay, so that spin accumulation is exerts a torque, or is able to exert a torque onto this ferromagnet that is at the surface, that is at the interface, and then with that you could even I mean, you change the magnetization dynamics. I mean, you modify the magnetization dynamics of that material of the ferromagnet, and you could also switch that magnetization in the materials, and that's what we're interested in. We're interested in having that level of control and manipulation of the magnetization on that ferromagnetic layer as a consequence of of the electrical properties, of the electronic properties of that TI. And then that effect is a consequence of the spin texture that you have at the electronic the electronic band of the TI because of that spin texture of the topological spin surface, the topological surface state. Sorry. And then those torques can be, of course, studied by a spin torque FMR. And then you analyze the signal that you get with this ferromagnetic resonance. And then you have different contributions. And then you analyze what kind of contributions. And then you have here a diagram of those different contributions, those different torques that are acting onto the magnetization of the ferromagnet. And then you see that depending on the shape of that on the component that you're analyzing of that ferromagnetic resonance, you have the symmetric component. It's more related to anti-damping torques. And the antisymmetric component has two kind of contribution. One is the Oersted field and the Oersted-like, and the other is the field-like torque. And as you see, they can even be opposite to each other. And what is the Oersted-like torque? The Oersted-like torque is the one that is just because you have a current as a consequence of just having a current passing through your system, through your metallic system. And the field-like torque is the one that you're interested in because is the one that comes from as a consequence of the Rashba-Alderstein effect at the interface. And then what you want to do is to make sure that your torque, or like that you want to optimize that torque to make sure that it comes from these, for the topological surface states, so that you exploit those properties of the TIs, right? And then what happens is that it has been reported for several systems of TIs with magnetic metallic layers that this could be, these field-like torques could be very strong, but not a very detailed or like a study or investigation of what happens at the interface. Whether there is intermixing or if there are other effects that could be affecting those torques that happen at the interface could be. We need to understand what's going on at the interface in terms of chemically as well, because that is affecting the electronic properties and the electrical and dynamics. So that's why in this study, what was done is that we use different spacers to explore those FMR properties and those spin orbit torques at the interface, just to make sure, how it affects those measurements of spin orbit torques. And then what we have seen is that, in fact, indeed, if you use different kind of interfaces like silver or aluminum or tellurium, you manage to gain efficient spin orbit torques, in particular with aluminum. And what happens is that if you have, because what happens is that you have intermixing at the interface. So it has been observed by TEM that you have an interfacial layer between the TI and, for example, permalloy or other metallic magnetic layers that is, of course, affecting the properties of those torques that you are exerting onto the magnetic layer. So in this case, what we did was to use X-ray photoemission spectroscopy to study chemically what happens at the interface. And so this is what I'm showing here. So here, let's take a look at what we see on these two kind of on these two spectra. So we have what is the position for the spectra for bismuth and tellurium for just single atoms of bismuth and tellurium. And this is what we see for bismuth telluride, when we have the alloy. So we see that there is, of course, a charge transfer between the two. So there is a shift on each of the peaks, right? But then when we have the bismuth telluride with permalloy, without any interlayer in between, what happens is that these peaks move towards those of the single atom, so which is which is not what you want. You want to have to recover the position of the alloy, and then we can do that by adding an interface. For example, if we add an interface of tellurium, a layer of tellurium, we manage to recover those positions, that chemical state of the tellurium and bismuth, which means that what happens when you have this interface of with permalloy is that the interface becomes tellurium poor in tellurium. Okay. But we are not, in terms of spintronics, in terms of spin transport and spin to charge interconvention, the tellurium is not the ideal. It's not an ideal because it absorbs too much the spin current. So you want a metal that allows for that spin current to go through and exert the torque onto the permalloy. So in that case, we went for aluminum, and then we see that with aluminum, we definitely have a component of this field light torque, which is the one that we are interested in, the one that we want to be more relevant in our measurements. So this is like the optimal interface, or like the optimal heterostructure for a spin orbit torque in these heterostructures. And well, just as a quick conclusion, intermixing plays a critical role in the generation of spin orbit torques at these interfaces. All right, so why is this interesting too? As I mentioned to you, we are also exploring some terahertz, ultra fast properties of these TI heterostructures. So just to give you a brief words about what we are trying to do now. We don't have results for this yet, but this is something as an exploratory study where we are taking these optimized layers, which have more efficient of a spin orbit torque and a spin to charge conversion, to explore terahertz emission devices that are based on spintronic devices. So because of the spintronic properties of these multi-layers, it has been demonstrated not only with metallic layers, but also with TIs, with metallic ferromagnets, that because of the spin to charge conversion of these interfaces, you are able to have emission in the terahertz range, which is interesting for applications of wherever you have terahertz can be of your interest. For example, for imaging or security, or like there is this bunch of new generation of fast electronics that are also interesting that are interested in getting more best and more optimal devices for terahertz emitters. So this is just to tell you that this is something that we are exploring, and this is a project that I'm leading at ICN2 right now. Okay, so this is in terms of metallic ferromagnets, but we can also study more proximity effects of the TIs with non-metallic ferromagnets, with insulating layers. And why is that? We want to study more proximity effects because we want to break time reversal symmetry in the material, in the TI, in order to induce, or like to introduce ferromagnetic order in that material, so that we can observe novel phenomena such as the quantum anomalous Hall effect. And also because it's also interesting to introduce this magnetic order in the TI, because those topologically protected surface states become spin polarized, and those can be even more attractive for spintronic applications. So we want to break time reversal symmetry, and we can do so by either applying a strong magnetic field or by doping with magnetic impurities, or by proximity with the ferromagnetic layers, which is what I'm going to tell you about, because we use some magnetic insulators because we don't want that, those surface state to be affected by the metallic character of the metallic layer. So we also explored like this, the use of for magnetic insulators to introduce magnetic order in the TI. And this has been studied since, since the advent of these TIs. Even since 2013, it has been observed, or like it has been investigated, that topological insulators interfaced with magnetic insulators can have very relevant or very, very strong proximity effects, magnetic proximity effects at these interfaces. And there have been lots of studies, not only in terms of experimentally, but also in theoretically, where novel phenomena, those interfaces have been explored, and of course you want to exploit those properties that are observed. And then in the case of europium sulfide, which is what I'm showing here, some results and some reports that have been during the past years, is that they have observed unusual magnetism at those interfaces of the europium sulfide with the TI. So even though the europium sulfide is magnetic down to, it has a Curie temperature of around 15 Kelvin. Some observations have shown that there is ferromagnetism at room temperature. Also, despite the fact that it is an in-plane, it has an in-plane anisotropy, some favorable out-of-plane magnetization has been observed. And then the most remarkable observation is that there is an enhanced magnetic signal inside the TI, within the TI. So this is something that has been explored using a series of characterization techniques, but is best to use one characterization technique that allows for this investigation at the local level, which is like X-ray absorption spectroscopies at synchrotron radiation techniques. And this is what we have done. So we have used X-ray magnetic circular dichroism to explore in an element and layer selective way what happens microscopically at the interface of this europium sulfide with the TIs, right? So because this, by exploring these core level transitions, we can study what happens at the europium atoms or what happens at the TI atoms. So the key questions to answer with this element selective magnetometry is that whether first, is there an enhancement of the europium magnetism at these interfaces? What is the anisotropy of the moments of that interface of the magnetic moments, in particular the europium moments? Whether there is an increase of the Curie temperature, because has been reported. And the most important part is whether there is induced magnetism in the TI, okay? And then for that, we grew our layers. So we grew, as I showed you on the MBE chambers that we have, we grew our topological insulator layers, which are of this bismuth, antimony, and tellurium, silurium family. So we grew a series of these samples, and then we transferred them in vacuum to the second chamber to evaporate europium sulfide on top. We had no additional phases. We have good quality of interfaces as demonstrated by XPS analysis as well. And then we took these samples to the synchrotron, and then we did our study. So we first studied what happens at the europium site. So we measured a series of samples of different TIs interface with the europium sulfide. So we measured at the europium M45 edges, and then we see that the europium atoms at this layer are mainly 2+. And then by analysis of the magneto-optical zone rules, we were able to extract the magnetic moment of the europium for all these samples, and then we compare with what is calculated for a europium 2+ spectra, and also what is reported for NDFT calculations, and we found no enhancement of the magnetic moment, or at least not above the error bar for XMCD measurements. And then furthermore, we also did some measurements as a function of the angle of incidence to study anisotropy. And then we saw that all samples have an in-plane easy axis of magnetization, not only on XMCD measurements, but also on the SQUID. I mean, the SQUID magnetometry, both the macroscopic and the microscopic magnetometry match, and they suggest that the europium atoms at the europium sulfide interfaces have an in-plane easy axis of magnetization, not an out-of-plane easy axis of magnetization. In terms of the magnetic order temperature, when we measured them with SQUID, we see that we don't see any difference between the single layer europium sulfide as compared with one europium sulfide interface with the TI. So we find the same Curie temperature around 15 Kelvin or so. And then that is also observed with the XMCD measurements, because we see that these layers are ferromagnetic at low temperatures and paramagnetic at 20 Kelvin. And then finally, we are interested in what happens magnetically at the TI, right? And that is one of the nice thing about XMCD, is that you can tune the energy to explore what happens at the magnetic order and magnetic character of the atoms in this layer, in the TI layer. So we tune the energy to the bismuth, antimony, tellurium, and selenium atoms of our TI layers. And then we basically found no evident XMCD signal. So we see that is quite noisy, and we found no XMCD signal above the noise level of the data measure. But even so, we applied the magneto-optical Stern rules to extract the magnetic moments for these atoms to establish an upper limit for the induced magnetic moment in these TIs, and we find that is below 10 to the -3 Bohr magneton, which is in strong contrast to what is reported for these layers, say, for example, for bismuth selenide interface with europium sulfide, because it has been reported that by polarized neutron reflectivity, they observed even 1 Bohr magneton at the bismuth and selenium atoms of these interfaces, which is really, really surprising. And then, well, this is in terms of europium sulfide. So we explored with other kind of, we studied these effects with other magnetic insulators. So we used, in this case, rare earth iron garnets, for example, yttrium iron garnet or thulium iron garnet, which are also magnetic insulators that have been used in interfaces with the TIs to study these proximity effects. Okay, and then there have been also reports of these polarization of spins at the interfaces within the TI at the interfaces with these iron garnets, with these magnetic insulators. So we grew our samples as well. In this case, we grew the iron garnet by pulse laser deposition on GGG substrates, on the gadolinium gallium garnet substrates, and then we took them to our MBE to grow the topological insulators on top, and then we grew our films. And then what we see, just a brief characterization of the magnetic layer. So our YIG samples are of very good quality, as revealed by this characterization like AFM or XRD. We have very good quality of the YIG. And also our gig is magnetic at room temperature, which is what we want. I mean, that's why we went for these garnets, which have also this magnetic character at room temperature. And then these, I mean, we grow our gig layers on at the here at ICN2, and then the ones the yttrium, I'm sorry, the thulium iron garnets are provided by collaborators of ETH Zurich. And then we took these samples to the, these layers, these yttrium iron garnets, to grow on the TI on top of the MBE. And in this case, we performed the two-step growth, which means that we start with a low temperature of the growth. Then we evaporate what we call a seed layer of the TI on top. And then on top of that, and then we anneal the sample to for a higher temperature of growth. And then we managed to recover and to continue the growth there of the TI. And then we managed to reconstruct the surface. And then we took our samples, our Hasse-Tree structures to the synchrotron to perform XMCD, and then to explore first what happens at the iron sites of the garnets, of the iron garnets. And then we observed a strong XMCD signal for all samples at the iron site. But then when we go to the TI atoms, again, we see no XMCD signal at these TIs in contact with these iron garnets, not even at low temperature. So these are like measurements at 20 Kelvin. And then, this is exactly what we found also for the europium sulfide, for the other magnetic insulator. And this has also, this behavior on iron garnets with XMCD has been also recently reported. But in that case, in this work, it's surprising that there's no XMCD, but there's still anomalous Hall effect. In transport, in magnetotransport measurements, you see some signatures of proximity effect. So it's important to understand what happens there. So there's something at the interface that is not well understood, or there's something that that we're failing to understand and to control at these materials. So further investigation is needed. So with this, I finished my first part of about the TIs. I just wanted to tell you that, to show you that we investigated TIs interface with the series of ferromagnets, metallic ferromagnets, to study spectroscopy and FMR measurements to study the spin-orbit torque. And then in that case, the main conclusion, or the take-home message, is that intermixing plays a critical role in the generation of spin-orbit torques at these interfaces, and that it is important to make sure we control such interface, not only in a chemical way, but also because it has an important and relevant, it affects what happens in terms of the spin-orbit torques that happen at the interface, and that is reflected into their spin-orbit properties. And then the second part was about the other materials that we use as interfaces with the TI was magnetic insulators, the europium sulfide and the TI. Europium sulfide and iron garnets. And then the take-home message in this case is that there was no clear signal on the TI atoms in contact with these magnetic insulators. And well, there are some ideas of what could happen. How can these results can be reconciled with the observation of a magnetic exchange gap that is observed in magnetotransport measurements. And it could be related to the sensitivity of the XMCD to small gaps, and also could be there are other ideas that says that it could be, since these proximity effects is very interfacial, and that might be diluted within the TI film thickness in this X-ray absorption spectroscopy experiments. All right, and then I'm going to finish with some results that we've got on 2D materials, and I go a bit faster because I'm running out of time. So just to give you, a brief introduction of what we do here. So in this case, we want to use graphene. Graphene is a is a prototypical 2D material, and it's interesting for spin transport because it has a large mobility, electronic mobility, and also you can tune the transport, and because it has a low spin orbit interaction, mean that those spins on the layer can travel long and without any, with very low diffusion. But very low losses. Not long diffusion lengths, but very low losses. But you cannot really control that spin transport in graphene because of that low spin orbit interaction. So you want to introduce some sort of spin orbit coupling in the material by proximity to high spin orbit material. You have to proximity to materials that have a high spin orbit coupling, such as transition metal dechalcogenides, which are materials that are also 2D. And then you can create these van der Waals heterostructures to make sure, to take advantage of both the electronic properties of the graphene and the spin orbit coupling properties of the TMDC. And then this has been studied in our group by colleagues in my group, where they have studied proximity-induced spin orbit coupling in graphene by investigating how is the spin relaxation, the spin transport in these in graphene TMDC heterostructures. And then they have observed that there is indeed an isotropic spin relaxation in graphene as a result of that proximity to a TMD. So you study the transport in two different geometries, the spin transport in two different geometries, and then you see that is characterized is an isotropic, and that results from that. That is a result of the spin orbit coupling that is being imprinted into the graphene because of proximity with the TMD. Another consequence is that you have spin to charge index conversion at these interfaces, and even up to room temperature, that is driven by that proximity to the TMD. So you find tunable spin Hall effect and spin galvanic effect on those interfaces, and this is all ways to demonstrate that you have spin orbit coupling that is being imprinted in the graphene from the TMD. But all these measurements are indirect. And then what I wanted to show you today is that using X-ray absorption spectroscopy, you have a way to detect, or like a way to observe such spin orbit coupling in graphene, or like in these graphene TMD layers, by analysis of these X-ray absorption spectroscopy. So we are, as I showed you in my previous, on the first part of my talk, if we use magneto-optical sunroofs for XMCD, we are able to extract the magnetic moments of a material, like of an element that we are probing. But if we go one step back, if we analyze the spectra, just like the X-ray absorption spectra, without without the application of a magnetic field, we find that there is a sunroof for this isotropic XAS that relates the integral of this absorption spectra with the angular part of the spin orbit interaction in this material. For example, here I'm showing the case of molybdenum, because I'm going to show you results about graphene interface with molybdenum disulfide. And then what we see is that XAS gives you a direct measurement of that spin orbit interaction if we analyze those spectra and with this sunroof of for isotropic SIS. That's what we did. So we took graphene MOS2 stacks, grown by chemical vapor deposition. The different layers were grown by chemical vapor deposition, and then then graphene is transferred on top of the MOS2. These are with collaboration of people from IMEC in Belgium. And then we took those samples to the synchrotron to study X-ray absorption spectroscopy. And then we studied at two absorption edges on layers, on stacks of graphene without the MOS2 and with graphene with the MOS2. And then first I'm showing here results of at the K edge of graphene. If we look at the carbon edge here, using linearly polarized light in order to see, to probe the different orbitals that comprise these graphene layers. And then, because depending on the geometry and the polarization, we are more sensitive to one one orbital or the other. So one orbital that is more out of plane, and another orbital, the pi orbitals that are in plane. And then we see strong changes in the spectra when we have one, for bare graphene and for the graphene interface with the MOS2, which means that indeed there are signatures of hybridization as a result of orbital mixing between the graphene and MOS2. And then we also did something similar at the sulfur K edge. So we see that there are clear changes. We see changes with with and without the graphene in this case for MOS2. And those are also features that are characteristic of hybridization. And such hybridization has been reported already in ARPES. And then, so it shows that, in ARPES, they see that indeed there are there's some features of those hybridization between the orbitals. And then in terms of the branching ratio, which is the one that we were interested in, we analyzed that for the molybdenum Mel2-3 edges. And then we see that, we extract the information by application of this some rule of the molybdenum. And then we see that there is a reduction in the branching ratio for the MOS2 graphene system as compared with the bare MOS2 without the graphene. And then that is related to a change in the spin orbit coupling in the system in these stacks. So this is like the main result in that case. And with this, I just finished finishing now. And I'm sorry for taking longer. Just to give you that, just to give you a take-home message, there is proximity effect on 2D materials, in this case of MOS2 interface with graphene, that is observed, that is evident in X-ray absorption spectroscopy measurements by analysis of different absorption edges. And with this, I just want to, I want to finish with the acknowledgement of everyone who is involved in all these works that I show you today. And of course, and also to funding agencies. And thank you very much for your attention. And I'm so sorry for taking longer than what I was expecting. Thank you.
So thank you very much, Adriana. I don't know if I can clap or somehow. Okay, it's not really, not very feel this Zoom to clap, but I'm sure everybody has enjoyed your talk. Thank you very much for a clear presentation and very nice experiments. Okay, there are some questions. Maria Angeles Laguna asked in Zoom, but now she's not there, so she's following this by YouTube, so I will read her question.
Okay.
It's about the growth of bismuth selenide europium sulfide bilayer. She says, do you grow these bilayers with the same orientation that in the paper where they see one Bohr magneton in the Nature paper?
Yeah,
Polarization
definitely.
could be very depending on that growth.
Yeah, definitely. I mean, despite the fact they don't use, I mean, we don't use the same substrate to grow the bismuth selenide. We compare the growth orientation is the same. It's the same as the 111 that we use. I mean, and then we compare our read images with theirs, and they're basically the same. I mean, in terms of structurally, they are comparable layers and interfaces. So that's why we are very surprised not to see XMCD signal on those interfaces. But yeah, definitely, I agree with her point about having a different orientation, and that could affect the observation of proximity effects. But we made sure that we follow the same recipe and the same and that we have structurally comparable layers.
Thank you. Thank you. David Serrate has also a question. I will allow him to ask directly.
Yeah. Okay. Thank you, Adriana. Really wonderful talk and wonderful job.
Thank you.
My question was about, maybe it's related with my complete ignorance on synchrotron radiation, but my question is about the interface magnetism of different kind of magnets, European sulfide or the garnets, in close proximity with the TI. Okay, so you are using XMCD as a main tool to probe the magnetism of the TI, but I would say that magnetism or magnetic textures on the TIs, they do not come to the core levels of the atoms, because it's very difficult to convince an atom which is not magnetic to be magnetic, to show a magnetic moment in the core levels. So maybe the approach should be something related with a less energetic probe and more focused to the surface state. So I wouldn't be surprised that you don't see anything on the core levels, and still the surface states, they display some kind of magnetic texture that provide the spin Hall effect.
Yeah, I understand your point. Yeah, but I'll see if I can show you. I don't know, because there is, I mean, the core levels that we explore on the here it is on the TIs is the for example on antimony or tellurium have been demonstrated to show magnetism on other kind of systems. I mean, in this family of TIs, like antimony telluride or bismuth antimony telluride, when we dope these materials, these TIs, with magnetic atoms, for example, with chromium or vanadium, or even with manganese, these core level transitions have, I mean, they have shown, or they have, they have revealed that they become polarized with these magnetic atoms. So that's why we said, okay, there is this precedent. I mean, there is this observation with magnetism and then induced magnetism at the tellurium and antimony. Let's try to check at these levels, because they are also the levels that are accessible at the equipment that we had at Alba, or at these beamlines where we did these experiments. So we were expecting to see signals. I mean, we knew what we were looking for, because we had these line shapes. I mean, we had these references for magnetic TIs. So we said, okay, there should be, or like we are expecting these levels, these electronic levels, to become polarized.
So. Okay, I see. Thank you.
Thank you.
Thank you very much, David and Adriana. So next question is by Jose Maria Teresa.
Hello, congratulations, Adriana, for the very nice talk. So I was wondering if you have characterized the bismuth selenide films with magnetotransport at low temperature, because if you study the weak anti-localization effect in films, you have a lot of information there. If you have conduction by the surface states, the top surface state, the bottom surface state, the bulk states.
Yeah, definitely. I mean, that is a very relevant question, because I mean, those are the, I mean, usually these magnetotransport measurements at low temperature, very low temperature, they have these characteristics. I mean, you can have these properties of weak anti-localization and so on. So we have not done that on our films, but we know, I mean, from reports that that it has been reported on this kind of materials, and then that these kind of reports suggest that there are proximity effects at these interfaces. So we have not done that in our films, but it's something that we are aiming at doing.
I think it's an indirect way to study this interface phenomena, because if you have very well characterized what is the contribution of your top surface with this weak anti-localization effect, then if, for example, you put a ferromagnetic insulator on top of that, you know it's not going to contribute to the transport, but if you modify your weak anti-localization signal, you can indirectly extract information of what's going on the interface. So it's just an idea.
Yeah, definitely. No, it's very relevant and very appropriate question and suggestion. Thank you, Jose Maria. Yeah, definitely.
Thank you very much, Jose Maria and Adriana. And I don't see any other questions, so maybe I can ask you.
Of course.
Yeah, I have been really amazed by this carbon KH spectra you have shown. This changes really dramatically from a pure graphene to what you expect from a two-dimensional sample to something that looks much more like a diamond spectrum. It's so it goes really to sigma, yeah, to the complete opposite way.
Yeah, we are very surprised, and this is work in progress. We're trying to analyze and also have some colleagues who are trying to do some simulation. I mean, some calculations of this spectra, which is not easy. I mean, for graphene, but yeah, we want to understand what happens. I mean, whether this is real or not, or because you have to have in mind that I mean, we want to analyze the main features that we see, but there might be contributions from other carbon, because you know, carbon is everywhere, so it's not an easy experiment to perform.
Yeah, but that is true indeed.
It's not an easy experiment. So in fact, what we do to make sure that we have a clean carbon is to anneal in situ the sample, just to make sure we have clean interfaces and clean. I mean, we clean, or like try to remove the carbon that is absorbed on top of the sample.
But so you are still trying to understand that you don't have a mechanism.
No, yet.
Or how does the molybdenum sulfide these on graphene?
No, we don't have an answer yet. These are preliminary results that we got. I mean, it's been a while since we have them, but we need the input from the theoreticians to see.
However, that's very interesting work for the future.
Sure. Yeah, indeed. Thank you. And also we want to explore this with other TMDCs, because that would be also, I mean, we have done this only for one for molybdenum disulfide, but if that happens with other TMDs, that definitely means that I mean, the effect is real.
Okay, so I don't see any other raised hand, nor questions in the chat or in YouTube. So I think I only have to thank you again. And well, that's the moment when the speaker, when the chairman says, let's thank the speaker again, and then everybody claps. And I don't know if we can clap really
thank you.
live, but I'm
thank
sure
you very
everybody would be doing so now in a normal condition. Thank you very much, Adriana.
Thank you very much, Fernando. So, and thanks to everyone for attending this online session. So thank you.
Gracias, Adriana. Gracias, Adriana.
Vale.
Gracias. Hasta
luego.
Gracias
A vosotros. Hasta luego. Bueno, pues me desconecto, ¿vale?
Vale, sí. He intentado desactivar el micrófono a todo el mundo, pero no he podido.
Perdón. Es que, claro, en el todo el mundo os incluye. Y,
vale.
Claro, debería haber un todo el mundo menos los que no son todo el mundo.
Bueno, muchas gracias.
Bueno, yo ya me desconecto. Muchísimas gracias. Me
Gracias,
alegra,
Adriana,
me ha hecho mucha ilusión.
Gracias.
No, a vosotros. Y ya siento que haya sido un poco más largo, pero bueno.